Hi, welcome to my talk on non-equilibrium self-assembly, predictions for worm-like micelles in flow. The purpose of this talk is 1. To describe a new framework for modeling out-of-equilibrium self-assembling systems in flow, and 2. Specifically, to understand the effects of extensional flow and shear flow on self-assembled systems of worm-like micelles. For the purposes of this talk, we're going to be focusing on a self-assembled system formed by surfactants in water and salt. Surfactant mixtures are known to be able to create all sorts of different self-assembled structures, and typically one thinks about these structures in terms of forming by a balance of entropic forces and enthalpic forces operating at equilibrium. But in practice, the structure of a material is formed by the course of its processing history as well, during which there are hydrodynamic forces at play. So the question is, once you have a flow or deformation, the system becomes out of equilibrium, and then what tools can we use in order to predict and engineer these structures that form? So for the purposes of this talk, we will be focusing on worm-like micelle structures. These are also known as living polymers. They are living in the sense that the polymerization reaction never terminates. The chains are continually breaking apart and attaching back together, hence living polymers. And at equilibrium, the scission energy, that is the free energy difference between a continuous chain and a broken chain, the free energy required to form two new free ends in that case, determines how long the chains will get. The higher the scission energy, the more costly it is to break the chains, the longer the chains will get. But what about a system under flow? Under flow, these chains are going to become stretched, and a stretched chain, one will think, is going to be more likely to break than a chain that has not been similarly stretched. So in this talk, we're going to develop a model to describe this kind of process. The first thing that we do, by way of review, is to look at the population balances. You consider all the possible structures that can form within your system, and you write population balance equations to describe the reactions by which a grouping of material will pass from one category to another category. In this case, since we're exclusively concerned with linear worm-like micelles, the only category is these different length categories, chains that are very short ranging to very long. And you can imagine that if you were to bin up that molecular weight distribution, as we've done with the figure on the left here, that every reaction when two short chains combine together, those chains move their numbers from a short chain category into a longer chain category. And when the long chain breaks apart, it moves material into the shorter compartments. And so you can consider the whole catalog of different reaction processes and the whole catalog of possible structures that can be forming in your system, and you can write out population balance equations for the self-assembling processes. Okay. Next, and this is what's new about our model principally, is that we also need to think about inside of each one of those bins, what is the typical configuration of the structure? And the configuration of the structure is going to relate to its stress and to its changes in its different reaction kinetics, right? So the conformation, the configuration or the stress inside of each one of these bins is going to be determined by processes including deformation, the applied flow on the system, relaxation. In the case of linear chains, are they reptating, are they retracting, these different kinds of processes. And finally, the interesting one for the purpose of our talks, reactions. So for example, one might imagine that longer chains, being longer, are less mobile and therefore take longer to relax their stress. So in a given flow, a longer chain is going to have more stress on it, typically, than a shorter chain. And when that long chain breaks apart, it's going to form shorter chain fragments. And it's going to move its stress from being in a long chain population into a short chain population. And likewise, when two short chains combine, they make the longer chain average stress lower. Okay, so the way that we model this for the deformation and the stress relaxation, we are going to use affine deformation and relaxation mechanisms borrowed from the roly-poly constitutive equation. So that includes relaxation by reptation, the first term, and relaxation by chain retraction and convective constraint release is the second one. Basically, these relaxation processes are thought to represent the dominant modes of stress relaxation in well-entangled linear polymers, both at low shear rates and high shear rates. So it's a very good constitutive equation for the kinds of well-entangled linear chains that we're interested in modeling in this talk. Okay, so having described the deformation and relaxation, the next step will be to look at the reaction terms. To do the reaction terms, we have to address the question of what is preserved in the course of a reaction. The first thing that's conserved is obvious, the total number of surfactants, or in this case we can also represent that as the total length of a chain. If you have a chain of length L1 and L2 that combine together, then the length of the product chain L3 is going to be equal to the sum of the lengths of the reactant chains. What's less obvious is that assuming the actual breaking event or connecting event is very fast compared to the typical timescales for stress relaxation across the whole chain, then one can approximate these attachment and breaking processes as adiabatic with respect to changes in the chain configuration. And in that case, you're going to have a configuration of the mean entanglement segment configuration, a conservation of the mean entanglement segment configuration during these reactions. So if Q1 represents the mean entanglement configuration in the first chain, Q2 is the mean entanglement configuration in the second chain, Q3 is the mean entanglement configuration in the third chain, you'll have this conservation relationship as this reaction occurs. And you can use that piece of information in order to describe how the mean configuration is changed by the reactive advection of stress throughout the system by virtue of these reactions that are taking place. So you go through the catalog of reactions that you have, all of the ways that chains can break apart, all the ways that they can attach, basically all of the ways that material can move from one structure into another structure. And you can describe, using population balance type equations, how those reactions change the mean configuration in any given sector of the molecular weight distribution. Okay, so the last piece that we need for the model that we're building here is to couple the equation for configuration to the equation to number density. In other words, how do changes in the configuration of a given structure affect its propensity to react along one pathway or another, moving into a different structure? So, first of all, for the forward reaction, when two chains combine together, what we're going to say is that considering well-entangled worm-like micelles, there should be basically no change in that case. And the reason for it is that the attachment process involves only the chain ends. And in well-entangled polymer materials, typically one assumes that the chain ends are more or less stress-free, isotropically oriented, in which case there's not going to be any change from the equilibrium reaction kinetics because the chain ends are essentially at equilibrium. The reverse reaction, however, in which chains break apart, the stretching that the flow causes these chains to become stretched, is going to lower the scission energy. So on the left-hand side of this figure, we have our test chain that we're looking at, and we're zooming in on one portion of the contour and examining the free energy density at that portion of the contour as a function of some reaction coordinate that takes the chain from being continuous to broken. So the lowest free energy locally there is for the chain to be continuous. But eventually you can get this necked state where the contour starts to thin, and if it thins beyond that point, it becomes more favorable for the chain to just break apart. And the difference between the energy of the broken chain and the continuous chain is called the scission energy, and the difference between the the broken chain and the necked chain is called the activation energy to scission. And if you were to have a chain that was stretched, then the energy for your continuous chain would be slightly higher due to that stretching. And that would reduce the total energy barrier to reach this next state and then ultimately proceeding towards the broken state. So it's that energy of stretching, if we assume an Arrhenius-like relationship between the free energy and the reaction kinetics, it's that energy of stretching that directly reduces the breaking rate constant. Okay, so we put that into our model, and then briefly I want to discuss, instead of working with the full equations, I want to talk about the fast breaking limit, namely, so where the typical chain will break apart before it has an opportunity to relax its stress by the full reptation type process, for example. Okay, the reason I want to look at this fast breaking limit is because the model simplifies quite substantially in this case. And it shows the same kinds of predictions, but I think it's easier to talk about and easy to understand what's happening in this limit. So, in the fast breaking limit, what happens is that reactions, chains being broken apart and reattaching, shuffle material across the molecular weight distribution so quickly that the stress on any chain of any length is typically going to look exactly the same, right? You're just taking the current stress in the system and you're shuffling it around before it has any serious opportunity to relax. Okay. And what that then means is that to the extent that chains have become stretched, you have increased the breaking rate constant, but you have done so uniformly across the molecular weight distribution. So the number density is still mono-exponential, but you have just changed the typical chain length in accordance with the change that you've introduced in your breaking rate constant, right? And then once you know that, you can describe the whole constitutive equation for this uniform configuration of all the chains, and your stress relaxation tensor is going to depend on the typical length of the chains in your system. So for example, as you make chains shorter, the typical relaxation time for those chains is going to become faster. Okay, so then rather than show all of the equations, I just want to do a brief run through of the dimensionless variables that emerge when you generate this set of equations. The first one is a parameter that we call theta, and that relates the rate of stretch relaxation to the rate of orientation relaxation, in particular at equilibrium. Larger values of theta give you systems that are more shear thinning in their rheology. Zeta gives the ratio of the stress of the breaking time, the time that it takes for a typical chain to break apart, relative to the stress relaxation time. So smaller values of zeta imply chains that break apart many times before they would otherwise have a chance to relax their stress by their built-in relaxation processes without breaking. The Weissenberg number is a dimensionless shear rate, basically. It compares the rate of strain relative to the equilibrium orientation time for the system. Alpha E is the size of an entanglement versus the size of a breaking site. So the more breaking sites you have on an entanglement, the more the stretching energy that you've introduced in an entanglement, it's kT per entanglement sort of thing, gets divided across all of these different possible breaking sites. So for smaller values of alpha E, that additional stretching energy is divided over fewer segments, you have more opportunities, you have a larger effect of flow-enhanced breakage in that system. And then beta is a parameter that's inherited from our roly-poly model, and it is a coefficient of effectiveness for the convective constraint release process, and it just relates to certain flow instabilities that appear if you go to small values of beta and large values of theta, for example. Okay, so let's begin with the nonlinear rheology predictions. We have the rescaled shear stress, which is the solid curve, and this dotted curve here, actually. And we have the dimensionless length of the chains relative to their equilibrium length. And that's plotted over a range of Weissenberg number. And this dotted curve here is shown for alpha E going to infinity. That's a chain for which flow-induced scission has no effect. So we're starting to see a departure. We're starting to see the effects of flow-induced scission around Weissenberg number comparable to the value of theta that we've chosen. We'll get to that in a minute here. Okay, so below Weissenberg number of 1, you have chains that are mostly relaxed, not really oriented, not really stretched. From Weisenberg number 1 to about theta, you have chains that are oriented but not really stretched. And then from Weisenberg number, for some range higher than that, you get chains that are stretched, but more or less you still have the same equilibrium molecular weight distribution. You haven't changed the average chain length because we have this large value of alpha E. You need some appreciable level of stretching before there's order KT change at each possible breaking site. And then beyond that, you start to see that the chains are sufficiently stretched by the flow, and the the molecular weight distribution, the typical size of a chain, starts to drop off. We can compare those predictions from shear flow to the predictions that one sees in extensional flow. The difference for extensional flow is that it doesn't have this rotational component that moves chains out of the axis of extension. So you'll always have chains being continually stretched in the direction of stretching and never rotated out of that direction. And that just means that you lose that window where there was stretching but not breaking. In an extensional flow, as soon as there is stretching, there is also flow-induced breaking for these well-entangled materials. Okay. So to summarize and review what we did in this talk, we developed population balance equations for the structures in the system, and then as a novel thing, we introduced population balance equations for the stress held by those structures as well. We then simplified the model to the fast breaking limit, where the essential behavior was preserved, and considered predictions of the model under extensional flow and shear flow and compared. And we found that under shear flow, there is a window where chains can become stretched but not have their molecular weight distribution appreciably changed, and that window does not exist in an extensional flow. So as a summary of some recent progress that we've done since the work described in this talk was originally done, we have extended the population balance approach for constitutive equations from single mode models, like the roly-poly model, into full chain constitutive equations. And that work has been accepted and will appear shortly in the Journal of Rheology. We've also done some work that shows that you can use these kinds of equations in CFD calculations, in spite of the fact that there's all these complicated integral population balance terms. We have spectral discretization methods that work great. And then future work on this subject may expand beyond linear chain worm-like micelles into branched polymer structures as well. Finally, I'd like to thank my PhD advisors under whom this work was originally done. That's Gary Leal and Glenn Fredrickson. And also thank my current postdoctoral advisor, Mike Cates, for his support and ongoing research in this area. So with that, I'd like to thank everyone for coming to this talk, for listening. I hope you enjoyed it. I hope you learned something new. If there's any questions or any interest in follow-up, please don't hesitate to contact me. I would love to engage and share more on this subject. Thank you for your time.